Hello, everyone. I'm very sorry we didn't have the chance to meet in Novi Sad, and I'm sorry I couldn't make the online session, so this is my recording. Let me just share the presentation. Okay, so my colleague um, Gorana Petković and I made an evaluation of some zipper tear strip design structures for paperboard packaging. So the zipper tear strip is usually used in packaging and in envelopes to have like an evident base, like a tamper-proof opening system. This is commonly used now even in food packaging. So here's a video with some examples. So on the left we see some different design types. It's usually developed on a way that it has cutting parts and uncut parts, and to achieve like a strip while opening. Sometimes some mistakes can happen. Paperboard can delaminate, or some layers can divide. This is going to be partially seen on the last example on the video, and using the fingers the way he does helps a lot with the opening system. So this is what we're trying to reduce, like to have a 100% opening system. Not much research was found, just one Japanese author with some papers in Japanese, so I couldn't translate them properly. And other available packaging literature rarely mentioned this type of opening system, which was really strange. So maybe I don't have enough access to literature, but if you have any information, please contact me anytime. So the issues with this type of opening is because it's cut through and around the packaging, it decreases the structural stability of the packaging, which means also the stackability, which is very important in corrugated cardboard packaging, which is partially sale packaging, partially transport. It needs to endure to transport and handling, and it has to have 100 openness success rate. To achieve an optimal design, to have all of the segments is the goal that we try to test, then the goal we try to achieve with designs. So the failure of opening is usually due to the delamination, which is mostly influenced by the design and the paperboard properties. But sometimes like totally bad design of the ZTS can influence the unsuccessful opening, and improper handling, like if it's under bad angle while opening. So one of the solutions the industry made was using a plastic strip underneath the ZTS, but this makes the packaging multi-layered. The additional manufacturing process makes the strip part harder to recycle. So there's an interest to achieve maximum opening success rate with adequate mechanical properties produced with less manufacturing processes, while keeping the recyclability of the packaging as a whole. So in Croatian supermarkets, this type is most commonly found, like over 90% of packaging that have opening tear strip will have this type of tear strip. And here are the variables we formed as a response to what we found in the market. So on the left, we have first the sample name, which is made with the distance of the blank part, the angle, and the width of the zipper style. We have the weight of the paperboard. So the D parameter here is the part between the cuts. It's usually 0 millimeters or a bit larger, 0.5 millimeters. The angles of the angle cuts were 30. We used 30, 45, and 60, but 30 wasn't found in the market. We just added it to see how will it uh, perform. And the width of the tear strip, it's 10 millimeters and 13. So those are the two values we found on the market. And the cutting parts, the angle part, it was almost always 3 millimeters, and the parallel part were 4 millimeters, the horizontal part. So here we also have the DIN grade, the thickness, and the manufacturer. And the test samples were cut on a flatbed cutter, Sunt M800, sorry, using a Z10 drag blade, which is a carbon blade which doesn't dull easily. So to achieve like the continuity of the samples. And the sample apparatus look like this. For the zipper pull test, we just had one sheet with the zipper with the zipper on it, and we had like a simulation of a small packaging. This was used for compression resistance and manual opening. The grain direction was always vertical, which is better for structural stability, and it's commonly used in packaging that direction. Uh, and this was glued using typical glue for packaging. So the zipper pull test was used with a gauge Mark 10. It measured the force needed to tear the zipper tear strip. Uh, it was a bit modified. We added a 3D printed platform, which made the sample start with a 40-degree pulling angle. And when the pull was finished, it achieved 90 degree according to the platform. So this was trying to simulate like a real life situation while pulling the strip mechanically. The speed was 3.5 millimeters per second, and 10 samples were for each design. The sample was also clamped on 4 positions, like we saw on the video of the guy using his fingers. The compression resistance, we put the simulated packaging in between two plates. It goes down at the speed of 0.8 millimeters per second, and it measures the force needed before the packaging, before the shape starts to bend. 6 samples for each design. We used this type of design because in some previous research we found that the longer panel results in a less compression resistant, not so good properties, but most packaging have more this type of shape than like a cube or any other. And the manual opening test was used with one user, same grip, same handling, 6 samples for each design, and it was used the previous samples were used also for the manual test. On the zipper pull test, we have a 100 success rate. There was no failure in openings. In both papers, we can see that the 45-degree angle achieved the highest resistance. And the 60-degree angle was the second best, with a few exceptions. Let me just see for there's like here at the start of the upper graph. I hope you can see my cursor. So, and the compression resistance test, we see there's a 40% reduction just by adding a zipper tear strip, which was mostly, and the results of the samples with the zipper tear strip are mostly unified. We can see just a small difference when we have, like in the lighter paperboard, when we have a 0.5 distance in between the cuts. We see maybe a bigger compression resistance. The same thing wasn't observed at the heavier paperboard, but we can see like a bell curve indicating that the 45-degree angle was much better than the 30 or 60-degree angle. The same thing is not seen at the lighter paperboard. It goes in all directions. And the manual opening test revealed that that it's not that perfect as in the mechanical openings when we're using a gauge. Here we have only three, like 30%, these two samples, and these two just 4 samples that achieved in both paperboards a 100 success rate. So it's not like the controlled pull test, and we didn't see any correlation between the samples with higher compression resistance and the successful opening. But here we can observe that the samples that had a wider ZTS had a bigger opening success rate than the ones with just 1 centimeter width. So the conclusions from this research is going to be that the ZTS decreases the compression resistance, the stackability of the packaging, which was expected. The 45 angle cuts are an optimal solution, and according to this research, the most functional design option. Wider 13 millimeters ZTS improves the successful opening rate when human handling, and there's an 0.5 millimeter increase between cuts might slightly improve the compression resistance. So this research could be improved by preparing samples using a die cut, not like a drag knife, which is more. But if it's a smaller amount of packaging made, then it's going to be probably used on a flatbed cutter. Also, future studies with other weights of paperboard, other types of paperboard, compared with other types of design, and to find an optional solution overall. So this is the idea for further research. These are the references, and as I understand, if you have any questions, you're gonna send it an email. So thank you all for listening, and I hope to see you next time.